Every atom in your body is evidence that something went wrong at the beginning of the universe. Not wrong in the sense of a broken machine, but wrong in the sense that the simplest outcome never happened. In the early cosmos, matter had an opposite called antimatter. Whenever the two met, both disappeared into radiation. The young universe was hot enough to create them together and dense enough to force them together again. If that balance had remained perfect, the final result would have been brutally clean. No stars, no planet, no ocean, no cells, no person listening to this sentence. Everything solid should have erased itself before the first atom had a chance to form. But the erasure failed. For roughly every billion pairs of matter and antimatter that destroyed each other, one extra particle of matter survived. One, that tiny remainder, became every galaxy we can see, every cloud of gas, every grain of dust, every bone in your body, and every electrical signal moving through your brain right now. You are not made from the main event. The main event annihilated itself. You are made from the residue, the almost invisible imbalance left on the floor after the universe should have cleaned everything away. And here is the part that turns this from a beautiful story into a genuine scientific crisis. We still do not know why that residue exists. Want to be precise from the first minute, because the title of this video uses the word flaw. Physics has not proved that the Big Bang made a mistake. Nature does not make mistakes in the human sense. The flaw is in the symmetry we expected, in the clean mirror our equations tempt us to imagine, and perhaps in our incomplete description of what happened. Something favored matter by an absurdly small amount. The preference was tiny enough to hide inside a billion annihilations, yet powerful enough to decide whether the universe would contain light alone or light plus everything that could ever look back at it. The entire visible world may exist because nature leaned by less than a whisper. That is the thread we will hold from beginning to end. First, we need to understand why antimatter is not science fiction, and why its collision with matter does not produce rubble but disappearance. Then we will return to the early universe and reconstruct the moment when almost everything was erased. After that, we will meet the three conditions any explanation for our survival must satisfy: the experiments that found part of the required asymmetry, and the uncomfortable reason those discoveries still appear too weak. We are not looking for a poetic answer to why anything exists. We are looking for a physical process that left one extra piece on the table. The ordinary world trains us to think that opposites cancel in a harmless way. Add a positive number and a negative number, and you return to zero. Mix hot water with cold water, and you get something in between. Matter and antimatter are more severe. They do not blend into neutral material. When a particle meets its antiparticle under the right conditions, their mass becomes energy carried by new particles, often photon. The original pair is gone. If an electron meets its antimatter partner, the positron, the meeting can produce light with the energy required by Einstein's relation between mass and energy. Nothing is lost, but the matter is no longer there. That distinction matters. Annihilation does not mean the laws of physics permit something to become absolute nothing. Energy, momentum, electric charge, and other conserved quantities still have to balance. What disappears is the identity of the original particles as matter and antimatter. Imagine two perfectly matched coins melting into a flash of light. The metal is not hidden under the table. It has been converted into another physical form in the early universe. This conversion happened on a scale beyond ordinary imagination. Matter and antimatter were not rare guests, occasionally colliding. They were part of a furious thermal crowd in which creation and destruction happened constantly. Antimatter entered physics before anyone caught it in a detector. In the late 1920s, Paul Dirac was trying to make quantum mechanics agree with special relativity for the electron. His equation worked with astonishing elegance, but it carried solutions that seemed to describe electrons with the wrong sign of energy. Physicists could have dismissed those solutions as mathematical garbage. Dirac took the equation seriously. After several conceptual turns, the strange solutions pointed toward a particle with the electron's mass and opposite electric charge. The mathematics had produced a mirror that nature had not yet shown us. A few years later, Carl Anderson studied tracks left by cosmic rays in a cloud chamber. Charged particle curved through a magnetic field, the way an electron would curve. except in the opposite direction. Its mass looked like the electron's mass. Its charge was positive. The positron had appeared not as a philosophical possibility, but as a visible trail through vapor. That discovery changed the status of antimatter forever. It was no longer a decorative consequence of an equation. The universe actually manufactured the mirror partner that the equation demanded, and cosmic rays were delivering examples from the sky. The pattern expanded. Protons have antiprotons, neutrons have antineutrons, quarks have antiquarks. For most particles in the Standard Model, there is a corresponding antiparticle with the same mass and opposite values for certain quantum properties. Some neutral particles are their own antiparticles, which complicates the picture. But the central mirror remains. Antimatter is not matter with negative mass, and it does not fall upward in any established experiment. It is ordinary physical substance, carrying reversed charges and quantum numbers. Recent measurements of antihydrogen are consistent with it falling downward under gravity. Just as careful theory expected, we can manufacture antimatter today. Particle accelerators smash energy into conditions when new particle and antiparticle pairs emerge. Medical scanners use positrons indirectly to build images inside the body. Laboratories trap antiprotons and positrons, combine them into antihydrogen, and study spectra that test whether matter and antimatter obey the same laws. These are not vague traces from the beginning of time. They are controlled pieces of the mirror world, produced and measured in rooms built by humans. The problem is not whether antimatter exists. The problem is why the observable universe contains so little of it in bulk. If antimatter were abundant around us, the sky would not hide it easily. A galaxy made of antimatter could look much like a galaxy made of matter from a distance, because antistars would still emit light. But where large regions of matter and antimatter touched, annihilation would produce characteristic high-energy radiation. Astronomers search for those signatures. They also search cosmic rays for anti-helium nuclei and heavier anti-nuclei that might point toward anti-stars or anti-galaxies. Few intriguing candidate events have appeared, but no confirmed population of nearby antimatter galaxies has solved the imbalance. The absence is not perfectly mapped across the entire cosmos, because the observable universe is enormous and our detectors are limited. We should not turn limited evidence into a declaration that no large antimatter domain exists anywhere but within the region we can study. Ordinary matter dominates overwhelming. The gas between stars is matter. The stars themselves are matter. Planets, meteorites, interstellar dust, and our bodies all share the same sign of baryonic material. If equal cosmic continents of matter and antimatter were interwoven nearby, their borders should glow in gamma rays. We do not see the required glow. Now, the mystery sharpens. The basic processes that create particles from energy tend to create matter and antimatter together. A photon with enough energy interacting in the right environment can help produce an electron and a positron. The reverse meeting can return their energy to photon in a hot thermal bath. These reactions can run in both directions. Creation replenishes the pairs, annihilation removes them. For a while, the population can remain in equilibrium, with no lasting victory for either side. The early universe was exactly the kind of environment where this traffic should have been relentless. Do not picture this as a bomb throwing particles into an empty room. The Big Bang model describes a universe whose space was expanding from a much hotter, denser state everywhere within our observable region. Temperatures were high enough for radiation to carry enormous energy. That energy could become particles. Particles could return to radiation. The universe was less like debris after an explosion, and more like a boiling physical economy in which currency changed form faster than any ordinary clock could follow. Matter was not yet organized into atoms, and atoms were not yet organized into anything alive. As the universe expanded, it cooled. That simple sentence drives almost everything that follows. Expansion increased the typical distance between particles and stretched the wavelengths of radiation, lowering its energy. At very high temperatures, photons could readily participate in making heavy particle pairs. As the temperature fell below the energy associated with a particle's mass, Creating new pairs became increasingly difficult. Annihilation could continue while replacement slowed. It was as if a factory stopped producing matched pairs, while the demolition crews kept working through the inventory already on the floor. If the inventory had contained exactly equal amounts of matter and antimatter, the demolition would have removed almost all of both. Small thermal residue might remain for a while, but the universe we know would never form. Instead, observations imply that matter held a tiny advantage before annihilation finished. When each antiparticle found a matter partner, the pairs vanished into radiation. The unmatched matter particles had nobody left to annihilate with. They survived not because they were stronger, but because they were extra. The universe ran out of antimatter before it ran out of matter. The ratio is difficult to feel because a billion is already beyond direct intuition. Imagine a stadium filled not with people but with matched red and blue grains. Each red grain destined to meet one blue grain and disappear. Fill the stadium, empty it through annihilation, then repeat that scale until the number itself becomes exhausting. After the matching is complete, almost nothing remains. Yet, for approximately every billion matched encounters, one unmatched grain stays behind. Build every star and planet from those lonely grains. That is the scale of the preference we are trying to explain. Now, reverse the comparison. Suppose the excess had been slightly smaller. Less gas would have remained after annihilation, changing how quickly gravity could gather material and perhaps delaying or suppressing the structures that followed. Suppose it had been much larger. The balance between matter and radiation would have changed, altering nuclear reactions and the later growth of galaxies. We should be careful here, because calculating complete alternate universes requires assumptions about many other quantities. The useful point is narrower. The observed asymmetry is not merely the difference between existence and emptiness. Its particular size became part of the initial inventory that every later cosmic process inherited. There is an important correction hidden inside the stadium image. Physicists did not watch this annihilation directly, and we cannot simply assume the initial universe contained perfectly equal piles. The measured fact is the present asymmetry, often expressed through the abundance of baryonic matter compared with photons or entropy. Simple symmetric starting conditions and the known behavior of particle creation make equality a natural expectation. But nature is not obligated to choose the simplest starting point. Perhaps the imbalance was built into the initial condition. Perhaps a process generated it dynamically. The name of the problem is not proof that equality once ruled. Still, a pre-written imbalance merely moves the question: if the universe began with more matter, why did it begin that way? Scientific explanation becomes stronger when it shows how an initially symmetric or nearly symmetric state can evolve into the measured asymmetry through physical laws. That process is called baryogenesis. The word refers to generating an excess of baryons, the family that includes protons and neutrons, over antibaryons. The detailed story may involve particles and energies far beyond those baryons themselves. But the output must be the same. More matter than antimatter survive. How do we know the size of the surviving excess? No line of evidence comes from the cosmic microwave background, the ancient radiation released when the universe became transparent. Any variations in that radiation carry information about the mixture of matter, radiation, and other components in the young cosmos. Baryonic matter affects how the hot plasma oscillated before neutral atoms formed. By measuring the pattern of hot and cold spots with extraordinary precision, cosmologists infer how much ordinary matter existed relative to the sea of photons. The result points to only a handful of baryons for every 10 billion photons. Second line of evidence comes from the first minutes, when nuclear reactions built light nuclei. The amount of ordinary matter changed how frequently protons and neutrons encountered one another, and therefore changed the predicted abundances of hydrogen, helium, deuterium, and lithium. Observations of ancient gas can be compared with those predictions. The agreement, though not flawless by every element, ties the baryon abundance to nuclear physics in a completely different era from the microwave background. Two cosmic fossils, light and chemistry, tell a compatible story about the small amount of matter that survived. This agreement is one reason the imbalance cannot be dismissed as a storytelling device. The number is not pulled from a philosophical preference for existence. It is constrained by patterns in the microwave sky and by nuclei forged before any star existed, the surviving matter abundance enters equations that successfully describe observations separated by hundreds of thousands of years of cosmic evolution. Whatever created the asymmetry had to operate early enough to shape those fossils, and it had to leave the universe in a condition that later produced them correctly. The word baryon also requires care. Most visible mass in ordinary objects comes from protons and neutrons, which are built from quarks. Proton contains a combination of quarks, while an antiproton contains the corresponding antiquarks. The asymmetry we observe can therefore be described through a surplus of baryon number, a bookkeeping quantity assigned oppositely to baryons and antibaryons. Electrons also had to remain in an amount that balanced electric charge on large scales. The complete cosmic accounting connects quarks, leptons, charges, and reactions, not merely two piles of finished proton. At this point, the problem might sound impossible. If physical laws treat matter and antimatter as perfect mirrors, no process can create a lasting preference from a symmetric state. Every reaction producing extra matter would have a mirrored reaction producing extra antimatter at the same rate. The gains would cancel, the universe would remain balanced, and annihilation would erase the structures we see. To escape that result, the mirror must fail in specific ways. In the 1960s, Andrei Sakharov identified three broad conditions a universe needs if it is going to manufacture a baryon asymmetry dynamically. Think of those conditions as three locked doors between a symmetric beginning and a matter-filled universe. Opening only one door is useless. The first requires processes that do not preserve baryon number perfectly. The second requires nature to distinguish particles from antiparticles through violations of certain symmetries. The third requires the universe to leave thermal equilibrium, preventing forward and reverse reactions from calmly undoing each other's work. Different theories build different machines behind the doors, but every successful baryogenesis proposal must confront the logic represented by all three. The first door is baryon number violation. In familiar low-energy life, baryon number looks almost indestructible. Protons appear stable. Nuclear reactions rearrange protons and neutrons, but do not casually erase the net baryonic count. If baryon number were absolutely conserved through every possible process, a universe beginning with zero net baryon number could never end with a positive value. You cannot produce a permanent surplus if the accounting rule forbids the balance from changing. Somewhere in the early universe, a successful explanation needs reactions capable of changing that ledger. The standard model contains a subtle opening at ordinary energies. Its interactions preserve baryon number extremely well, but non-perturbative electroweak processes can violate baryon plus lepton number under extreme conditions. These processes are associated with configurations often discussed through sphalerons. They are negligible in the cold universe around us, yet they could have been active when the electroweak force operated in the hot early cosmos. That matters because it proves baryon number is not necessarily an eternal wall inside known physics. Under the right conditions, the ledger can change. There is also a more dramatic possibility: proton decay. Many theories extending the standard model predict that protons are not perfectly stable and can eventually decay through interactions that violate baryon number. Experiments place enormous tanks deep underground, watching vast numbers of protons for rare flashes that would reveal such a death. So far, no confirmed proton decay has appeared. The limits tell theorists that simple versions of grand unified models cannot work as first imagined, but the search continues because one proton dying in the right way would open a direct window onto physics capable of rewriting baryon number. The first door alone cannot choose matter. Reaction that changes baryon number but treats particles and antiparticles identically will create baryons and antibaryons in matching amounts. The ledger moves locally and returns globally to zero. This brings us to the second door, which is really a pair of related locks. One is called charge conjugation symmetry, abbreviated C. It asks whether the laws look the same after replacing every particle with its antiparticle. The other combines charge conjugation with parity, the operation that reflects spatial directions, as in a mirror, if both C and the combined CP symmetry were exact. the cosmic factory would remain impartial. Any path-making matter would have a mirrored path-making antimatter with the same probability. Sakharov therefore required violations of those symmetries. Nature must contain reactions where the rate for particles differs, even slightly, from the corresponding rate for antiparticles. That sentence is the conceptual heart of the title. The universe needs a flaw in the mirror. Not a large flaw. Microscopic preference repeated through a vast number of reactions can leave the tiny surplus that later becomes everything. The discovery that parity symmetry fails had already shocked physics. For years, many researchers assumed nature would not distinguish left from right at a fundamental level. Experiments involving weak nuclear decay showed otherwise. The weak interaction can recognize handedness. Mirror-reflected process is not always physically equivalent to the original. That was a profound crack in the old expectation of symmetry. But parity violation by itself does not guarantee that matter will defeat antimatter. The combined transformation involving particles, antiparticles, and reflection seemed for a time to restore the balance. Then neutral kaons broke that comfort. Kaons are particles containing a strange quark or antiquark combined with another quark component. Neutral kaons can transform into their antiparticles and decay through the weak interaction. In the 1960s, experiments found that the decays did not obey CP symmetry perfectly. The effect was small, but it was real. Nature did not treat the mirrored particle history as exactly equivalent. The door Sakharov needed was not merely theoretical. Measured process had opened it by a crack. This is one of the moments in science where a tiny deviation carries an enormous emotional weight. Detector records a small excess in one decay pattern. The number looks like a nuisance hiding after the decimal point, but conceptually, it says the universe contains a lawful distinction between matter and antimatter. The mirror is not perfect. The dream of baryogenesis becomes physically plausible. We can point to a real asymmetry in laboratory data and say that at least one ingredient required for our existence is present in nature. There is another symmetry called CPT that helps clarify what was and was not broken. It combines charge conjugation, spatial reflection, and reversal of time under the basic assumptions of relativistic quantum field theory. CPT symmetry is expected to hold, and experiments test it with great precision. P violation does not mean every relation between matter and antimatter collapses. It means the mirror involving charge and space can fail while a deeper combined relation survives. Nature is not abandoning order. It is using a more intricate order than the simple mirror first suggested, leaving enough room for particles and antiparticles to follow measurably different histories. Later experiments found CP violation in systems containing bottom quarks, especially neutral B mesons. Large detector collaborations built machines designed to produce enormous numbers of these particles and compared their decays with those of their antiparticles. The observed patterns agreed impressively with the framework encoded in the standard model through the quark mixing matrix. Matter and antimatter traced slightly different routes through probability. The asymmetry was no longer an isolated curiosity of kaons. It was part of the established architecture of weak interaction. Experiments have continued with other mesons, including particles containing charm quarks, while dedicated facilities and collider detectors refine the measurements. Arc result tests whether the standard model's single known phase responsible for quark sector CP violation accounts for the data or whether an extra discrepancy appears. The work is painstaking because the effects can be small and detector biases can imitate differences. Researchers reverse magnetic fields, compare control channels, and process extraordinary event samples to separate nature's preference from the instrument's preference. Here comes the disappointment that keeps the mystery alive. The CP violation measured in the standard model appears far too weak to generate the observed cosmic matter excess under the known early universe condition. The exact calculation depends on the process and assumptions, but the qualitative problem is robust. We found a flaw in the mirror, yet not a flaw large enough to build the visible universe. It is as if investigators found a leaking pipe at a flooded building, calculated the leak, and realized it could not have supplied more than a tiny fraction of the water. This does not make the discoveries irrelevant. They prove nature can discriminate between matter and antimatter, and they give us a precise framework to test, but they also sharpen the missing physics problem. Universe governed only by the measured standard model ingredients seems unable to lean far enough toward matter. Somewhere, either an additional source of CP violation exists, the early universe transition behaved differently than simple calculations suggest, another mechanism amplified the preference, or the asymmetry entered through initial conditions we do not yet understand. The third, Sakharov door, explains why even a preference can fail to survive. In complete thermal equilibrium, every reaction is balanced by its reverse. If one process converts a set of particles into another set, the surrounding bath provides reverse collisions at rates that restore the equilibrium population. Detailed balance acts like a tireless accountant. Temporary excess can arise in one corner, but the reverse traffic washes it away. To freeze a net asymmetry into the universe, conditions must change fast enough that the erasing reactions cannot keep up. Expansion provides the broad opportunity. As the universe grows and cools, reaction rates can fall below the expansion rate. Particles that once collided constantly become too sparse or too cold for certain interactions to remain effective. Species can fall out of equilibrium. Phase transition can move fields from one state to another. Heavy, unstable particles can decay when the reverse process is no longer common. The cosmic factory does not merely slow down. Some production lines stop before the demolition crews can restore the old balance. Think of wet concrete moving on a conveyor belt. Higher workers can continuously stir it. Any pattern pressed into the surface disappears. If the belt carries the concrete into a cold region before the workers smooth it, a temporary mark becomes permanent. Thermal equilibrium is the stirring. Expansion and cooling move the material away. P-violating reactions press a preference into it. Barrier number changing processes translate that preference into a real surplus. Remove any one of those roles, and the finished universe carries no lasting imprint. The standard model contains versions of all three ingredients in some form. It allows electroweak processes that can change baryon and lepton bookkeeping. It contains CP violation in quark interaction, and the expanding universe certainly moved through changing temperatures. That sounds as if the case should be closed, and the quantitative details betray us. The measured CP violation is too small, and with the known Higgs boson mass, the electroweak transition in the minimal standard model is not expected to provide the violently out of equilibrium first-order transition that simple electroweak baryogenesis would need. This is why the matter-antimatter problem is so valuable. It does not merely say our knowledge is incomplete in a vague philosophical way. It points to specific missing capabilities. We need enough asymmetry in reaction rates. We need the correct kind of departure from equilibrium. We need a mechanism that survives washout processes and produces the baryon abundance inferred from cosmic fossils. A proposed theory must run this gauntlet numerically. It cannot win by sounding profound. It must leave approximately the right amount of matter and avoid ruining everything else particle physics already explained. One family of ideas tries to repair electroweak baryogenesis. The electroweak force unifies electromagnetic and weak behavior at high energies, then takes on the broken form we know as the universe cools. If that change happened through a strong first-order phase transition, bubbles of the new phase could have formed and expanded through the old phase. Their moving walls would create an environment out of equilibrium. New sources of CP violation near those walls could separate particle behavior from antiparticle behavior. Picture bubbles forming in boiling water, but do not take the analogy too literally. These would be regions where the Higgs field and related fields occupied a new physical state. As bubble walls swept through the plasma, particles interacting with the wall could experience CP-violating effects that generated an excess in front of it. Electroweak follow-on processes could convert part of that excess into baryon number. Once the wall passed and the new phase settled, the conditions could suppress further erasure, trapping the baryon asymmetry behind it. The minimal standard model does not seem able to make this transition strong enough, but additional particles or an expanded Higgs sector could change the shape of the transition. That possibility makes electroweak baryogenesis attractive because some of the new physics might live near energies accessible to colliders or influence Higgs properties with measurable precision. The same cosmic question about why matter exists becomes connected to laboratory searches for extrascalar particles, subtle deviations in Higgs interactions, and patterns of CP violation not predicted by the current model. Strong early-phase transition might also generate gravitational waves. Colliding bubbles and turbulent plasma could disturb spacetime in characteristic ways, leaving a background that future detectors might probe. This does not mean any gravitational wave signal would prove baryogenesis. Many processes can produce backgrounds, and model predictions vary, but it creates an extraordinary possibility. Preference that helped matter survive before atoms existed might have shaken spacetime, and an instrument built billions of years later might hear the residue of that transition. Electroweak baryogenesis therefore offers something scientifically healthy. It is imaginative, but it is not protected from evidence. Collider measurements can squeeze its new particles and interactions. Electric dipole moment searches can constrain new CP violating phases. Gravitational wave observations can test some transition scenario as the constraints improve. Entire versions of the idea can die. Theory that risks death is doing real scientific work. The difficulty is that no current measurement has selected this family as the mechanism nature actually used. Another major family begins with leptons, rather than baryons. This proposal is called leptogenesis. Leptons include electrons and neutrinos. The key idea is that a process in the very early universe first generated an asymmetry between leptons and antileptons. Electroweak Sphalerone processes then redistributed part of that imbalance into baryon number. Matter wins indirect. The original preference may have appeared in a sector that seems almost invisible in everyday life, and then being converted into the protons and neutrons that build the visible world. Neutrinos make this route especially compelling because they already refuse to fit neatly into the simplest standard model story. Experiments show that neutrinos oscillate between types, which implies they have mass. The minimal version of the standard model originally treated them as massless. Their tiny masses invite new ingredients, possibly heavy right-handed neutrinos that interact far more weakly than familiar particles. If such heavy neutrinos existed in the early universe, their decays could occur out of equilibrium and could violate CP, producing more leptons than antileptons. The heavy particles in many leptogenesis models would be far beyond direct production in present accelerators. That makes the proposal difficult to test cleanly, yet it connects to questions we can approach. Are neutrinos their own antiparticles? Particles known as Majorana particles. How are neutrino masses generated? Does the neutrino mixing system violate CP? Experiments sent neutrino and antineutrino beams across long distances, watching how their types change, searching for differences that may reveal a new source of asymmetry. One especially important search looks for a nuclear process called neutrinoless double beta decay. Ordinary double beta decay emits electrons together with antineutrinos. If a decay occurred without the neutrinos emerging, it would suggest that a neutrino can act as its own antiparticle, and that lepton number is not perfectly conserved. That would not identify leptogenesis by itself, but it would reveal exactly the kind of new bookkeeping behavior the proposal can use. Huge detectors isolate carefully chosen materials from background radiation, waiting for an energy signature so rare that years of silence are expected. Even a clear measurement of CP violation among ordinary neutrinos would not automatically prove leptogenesis. The phases accessible at low energy may not be the same combinations controlling the decay of hypothetical heavy neutrinos. Different models connect them differently. This is where popular explanations often move too quickly, turning a suggestive bridge into a completed highway. The honest statement is more restrained. Neutrino physics provides a natural arena for additional asymmetry, and leptogenesis provides a coherent mechanism. But the decisive chain from measured neutrinos to cosmic baryons remains unconfirmed. There are other baryogenesis proposals, but listing them all would make the central mystery thinner rather than deeper. Some involve grand unified particles whose decays violate baryon number directly. Some use scalar fields evolving coherently in the early universe. Some connect the asymmetry to dark matter, trying to explain why the abundances of visible and invisible matter have comparable cosmic scale. These possibilities matter yet the logic underneath them remains Sakharov's logic. Change the ledger, break the mirror, and leave equilibrium before the preference is erased. The search for additional CP violation extends far beyond meson factories. Ni powerful approach looks for permanent electric dipole moments in particles such as the neutron, electron, atoms, and molecules. An electric dipole moment would mean positive and negative charge distributions are separated along a particle's spin direction. For a fundamental particle, a non-zero value can signal violations of symmetries connected to time reversal and CP. The standard model predicts extremely tiny effects in many systems. Larger measured dipole could reveal precisely the new physics baryogenesis needs. These experiments are masterpieces of patience. Researchers isolate particles from magnetic noise, cool molecules, control electric fields, and watch for minute changes in spin precession. The sought signal can be smaller than disturbances caused by imperfections. No human senses direct that every improvement that finds nothing is not an empty result. It rules out ranges of CP violating new physics and forces baryogenesis models into narrower territory. The universe clearly achieved an asymmetry. Our laboratories keep asking which hidden interaction was strong enough to do it, without exposing itself elsewhere. Collider experiments perform a complementary search. They compare the production and decay of particles and antiparticles, test Higgs interactions, and look for new particles that could reshape the electroweak transition. So far, the standard model remains frustratingly successful across an enormous range of measurements. That success is both triumph and trap. The model describes known accelerator data remarkably well, yet it appears unable to explain why enough matter survived. The missing ingredient either hides at higher energies, couples too weakly for easy detection, or appears through a structure our searchers have not targeted correctly. Proton decay experiments test another side of the first Sakharov door. If a grand unified interaction converts quarks into leptons, a proton could decay with a characteristic pattern. Decades of null results have pushed possible lifetimes to extraordinary scales and eliminated elegant early models. Future detectors will watch even larger quantities of matter with improved sensitivity. A single convincing event, repeated with the expected signatures, would transform the baryogenesis landscape. Until then, baryon number violation remains theoretically motivated but experimentally elusive outside the special electroweak processes. There are also searches for neutron-antineutron oscillations, in which a neutron might transform into its antiparticle through a process-changing baryon number. Such an event would be astonishing. It would demonstrate that the distinction between baryonic matter and antimatter can blur dynamically, and it would provide new ingredients relevant to early universe asymmetry. Experiments study free neutrons or bound neutrons inside nuclei, looking for disappearance and annihilation signatures. No confirmed oscillation has appeared, but the possible connection to our existence keeps the search alive. Cosmology tests the story from the opposite direction. The microwave background and light element abundances constrain the final baryon yield. Searches for primordial gravitational waves can probe violent early transitions. Measurements of antimatter in cosmic rays test whether unusual antimatter sources exist nearby. Gamma-ray observations constrain large matter-antimatter boundaries. ACK method touches a different part of the chain. None can replay baryogenesis like a recording. Together they reduce the space in which an explanation can hide. The difficulty is that the decisive events likely occurred at energies and times inaccessible to direct observation. We receive no ordinary photon from the epoch when baryogenesis may have happened. The universe was opaque, and interactions were too dense. We work like investigators arriving after a fire has consumed the building, using surviving ash, warped metal, and chemical traces to infer the first spark. The baryon abundance is the ash. Particle asymmetries are marks on the metal. Candidate theories reconstruct sparks that might produce both without contradicting the rest. Washout is one of the investigators' hardest problems. Theory can generate a beautiful asymmetry and still fail because later reactions erase it before the universe cools enough to protect it. The calculation must therefore follow production and destruction together as the temperature changes. Heavy particles appear, decay, scatter, and disappear. Follow-on processes switch between effective and ineffective regimes. Entropy dilutes abundances. Successful model cannot merely create baryons in one dramatic instant. It must escort the excess through every later danger until nuclear physics and cosmic expansion lock the surviving amount into the history we observe. Could antimatter be hiding beyond our observable horizon? Balancing the universe as a whole, it is possible to imagine cosmological regions with opposite asymmetries, especially in models where conditions vary across domains. If those regions are causally disconnected from us, local observations may never reveal them, but that possibility does not erase the local problem. Our observable patch contains a large matter surplus, and some initial condition or dynamical process must account for it. Global balance elsewhere would not explain how our domain acquired its sign and magnitude. Could the answer simply be chance? Quantum processes contain probabilities, and inflationary cosmology may generate enormous domains. Perhaps different regions acquired random signs of asymmetry, and observers naturally appear only where enough matter survive. This family of reasoning can be internally consistent in some models, but it still needs a mechanism defining the random field, its fluctuations, and the resulting domain structure. Chance is not the absence of physics. Scientific appeal to chance must specify the lottery, the tickets, and the distribution from which our result was drawn. Could the asymmetry have existed from the first describable moment, S, and no observation currently forbids every version of that possibility? But an unexplained initial condition is not the kind of answer. Physicists usually stop at when a dynamical explanation might exist. Saying the universe began with extra matter protects the observed fact, while abandoning the attempt to derive it. Sometimes initial conditions are fundamental. Sometimes they are placeholders for deeper processes. We do not yet know which role the baryon asymmetry plays. There is another conceptual trap in the phrase, one extra particle per billion. The actual thermal history involves different particle species, changing degrees of freedom, quark confinement, and entropy transfer. The simple ratio is an accessible picture, not a frame-by-frame photograph. At high temperatures, the relevant excess lived among quarks and perhaps leptons, not finished protons waiting beside antiprotons. Later, quarks became confined inside baryons, electrons balanced charge, nuclei formed, and photons cooled. The survivor story remains valid, but the cast changed costumes many times. Quark confinement deserves a moment because it connects the invisible asymmetry to the material world. As the universe cooled, free quarks and gluons became bound into composite particles. Three quarks could form a baryon such as a proton or neutron, while antiquarks formed antibaryons. The pre-existing tiny excess of quarks meant that after quarks and antiquarks annihilated and confinement reorganized the survivors, baryonic matter remained. The asymmetry passed through a major transformation without losing its sign. Preference born in particle reactions became the inventory for nuclear chemistry. Minutes later, some protons and neutrons fused into light nuclei. Much later, electrons joined nuclei to form neutral atoms. Gravity gathered gas into stars. Stars forged carbon, oxygen, silicon, and iron. Exploding stars and stellar winds distributed those elements into space. New stars and planets formed from the enriched debris. Chemistry built molecules, and on at least one planet chemistry became biology. Every step is a separate scientific story, but every step inherited the same admission ticket. None could begin unless baryogenesis had first left matter on the stage. This is why calling the asymmetry tiny can be misleading. Ini describes the fractional preference before annihilation. It does not describe the consequence after annihilation. Once the matched majority disappeared, the tiny excess became 100% of the remaining matter. The loser of the first comparison became the entire later inventory. Difference, almost invisible while the room was crowded, became absolute when the room emptied. Scale changes, meaning the residue of one era becomes the total substance of the next. There is a lesson here about how physics creates enormous outcomes without enormous initial pushes. Pencil balanced almost perfectly can fall left or right because of a disturbance too small to see. The direction later becomes obvious. Even though the original bias was microscopic, the matter-asymmetry is not exactly that kind of spontaneous breaking, and we should not confuse analogy with mechanism, but the image helps with consequence. The universe did not need matter to defeat antimatter by a landslide. It needed the smallest durable lead before the counting stopped. We should also resist turning matter into the hero and antimatter into the villain. From the perspective of the laws, antimatter is not destructive evil. An antimatter observer in an anti-galaxy would likely call their own substance matter and ours antimatter. Their chemistry could mirror ours. Annihilation is mutual. Neither side survives the meeting. Our emotional loyalty to matter comes from the accident that matter is what we are made of. The scientific question is not why good defeated bad, it is why either sign obtained a numerical advantage. That point makes the asymmetry even stranger. Many fundamental properties appear identical in magnitude for particles and antiparticles. The electron and positron have masses equal to extraordinary precision. Hydrogen and antihydrogen spectra are tested for differences, and none has overturned the expected symmetry. Antimatter appears to obey gravity normally within current precision. The universe preserves the mirror beautifully in many places, while violating it subtly in the processes relevant to CP. The cosmic outcome is lopsided, even though the components look almost perfectly paired. This pattern is what makes the mystery scientifically productive. If antimatter behaved wildly differently in every experiment, explaining its cosmic absence might be easy. Instead, the mirror holds almost everywhere we look, then fails in narrowly defined weak interaction. The known failures are real but insufficient. We are searching for another narrow failure, hidden well enough to preserve decades of precision tests, but strong enough in the early universe to determine the existence of galaxies. The allowed hiding place becomes smaller with every experiment. What would count as a satisfying solution? Ideally, one theory would identify new particles or fields, show how they behaved in the hot universe, calculate a baryon excess matching cosmological observations, and predict independent laboratory or astronomical signals. Those signals would then appear with the correct relationship. Perhaps a new CP violating phase would be measured alongside an electric dipole moment. Perhaps neutrino properties would support a specific leptogenesis model. Perhaps collider data and gravitational waves would point to the same electroweak transition. Agreement across independent evidence would turn a candidate into an explanation. We are not there. Electroweak baryogenesis remains a family of possibilities under pressure. Leptogenesis remains compelling but difficult to connect uniquely to accessible measurements. Grand, unified mechanisms remain constrained by the silence of proton decay detectors. Other models can reproduce the asymmetry with enough adjustable ingredients, but reproducing one number is not enough if the theory predicts nothing else. The honest scientific position is not that all ideas are equally likely. It is that no mechanism has yet earned the right to be called the historical answer. That uncertainty does not weaken the central fact. Ordinary matter exists in a universe where antimatter partners are real, annihilation is real, and the observed abundance demands a profound early imbalance. We know the residue survived. We know some CP violation exists. We know the standard model contains baryon-changing electroweak processes under extreme conditions. We know expansion carried the universe away from its earliest equilibrium states. What we do not know is whether those known ingredients combined in an unknown way, or whether new physics supplied the missing strength. Return now to your hand. Its atoms contain nuclei built mostly from the baryonic residue. The electrons around those nuclei belong to the accompanying charge balance that also survived. The carbon in your cells was forged in stars, but the quarks inside its protons trace their material ancestry farther back than any star, back toward the excess that escaped annihilation. When you move a finger, matter left over from the first fraction of cosmic history rearranges itself and asks why it was left over. The title says, One flaw created everything. The scientifically careful translation is this: mean tiny asymmetry allowed everything made of ordinary matter to exist. It did not create dark matter, dark energy, space-time, or the laws themselves. And we should not pretend it solved every origin question, but it created the surviving material inventory, from which every visible structure around us was assembled. Without that preference, the universe might still contain expanding radiation, and whatever other components survive, it would not contain the baryonic world that tells stories about it. Perhaps the answer will come from a particle no detector has yet seen. Perhaps neutrinos carry the decisive clue. Perhaps a phase transition shook space-time and left a signal waiting for a future observatory. Perhaps the asymmetry is tied to physics at energies we can never reproduce directly, forcing us to triangulate it from indirect traces. Or perhaps our demand for a dynamical origin will fail, and the imbalance will remain part of the universe's initial condition. These possibilities are not interchangeable, and experiments are slowly separating them. What makes the problem unusually personal is that failure would have erased the investigators. Most unsolved questions describe features of a world that would exist whether or not we understood them. This one asks why there was enough material for observers to arise at all. That does not mean consciousness explains the asymmetry or that the universe intended. It means selection gives the problem an intimate angle. We can only wonder about baryogenesis from a region where baryogenesis, or something equivalent, succeeded. Do not turn that intimacy into proof of purpose. Physics has found no evidence that the matter excess was arranged for life. Tiny asymmetry can be the consequence of impersonal fields and decays. The later appearance of observers does not reach backward and cause the process. The honest wonder is strong enough without adding intention. Blind physical laws may have leaned slightly. Annihilation may have amplified the consequence, and billions of years later, the residue became capable of noticing the lean. We began with the claim that every atom in your body is evidence. Something went wrong. We can now repair the sentence. Every atom is evidence that perfect matter-antimatter balance did not determine the fate of our observable universe. Somewhere in the history we cannot directly photograph, nature selected an excess. Known physics shows several pieces of how such a selection could happen, but not enough to reproduce the measured result with confidence. The flaw is real as an asymmetry. Its cause remains missing. If you leave with only one image, keep the empty stadium after the matched grains are gone. Almost every particle has found its opposite. Almost every piece of material possibility has become radiation. The seats look empty until you notice one unmatched grain after each impossible crowd of pairs. Gather those grains across the expanding cosmos. Gravity pulls them into clouds. Stars ignite. Planets form on one of them. The residue builds eyes, hands, and a brain able to reconstruct the annihilation it escaped. That is the deepest reversal in this story. We usually imagine ourselves as complicated products added near the end of cosmic history. In one sense we are, but the material permission for our existence was decided near the beginning, before stars, atoms, and chemistry. Everything life later accomplished depended on a numerical preference so small it would disappear in ordinary rounding. The universe did not need a large supply of matter after its great annihilation. It needed a remainder that was not exactly zero. The experiments continue because zero and not zero are different universes. Slightly improved dipolar measurement, a rare neutrino pattern, a forbidden proton decay, a new Higgs interaction, or a gravitational wave background could change which origin story survives. Most searchers will report limits rather than revelations. That is normal. Arc limit removes another hiding place from the mechanism that made visible existence possible. Patiently, indirectly, physics is asking the residue to reveal how it escaped. Until it does, the matter around you carries an unanswered question in every nucleus. Not a vague question about meaning, but a technical question with measured inputs, symmetry requirements, candidate reactions, and experiments capable of killing wrong answers. Why did matter outnumber antimatter? Why was the excess at the level we observe? Each process opened all three Sakharov doors at once. We know what a successful answer must accomplish. We do not know which piece of nature accomplished it. The next time you look at an ordinary object, remember that ordinary is the final disguise of something wildly improbable. Look-in. Table seems stable. Stone seems inevitable. Your hand seems like the default kind of substance. None of them is the default outcome of perfect annihilation. They are survivors assembled from a cosmic imbalance. Durable evidence that the mirror failed by just enough. The visible universe is not the triumphant majority of the beginning. It is what remained after the majority disappeared. Thank you very much for joining me on this journey through the cosmic mysteries. And until next time, keep looking up.